Okay, so today in this class we are going to discuss simulating probabilistic behavior using Monte Carlo method. Acha. The probabilistic behavior means let me just give some specific examples such as coin toss, throwing a dice. These are all probabilistic behavior because we have already discussed कि whenever we say suppose a toss a coin, until and unless you are getting the output, you do not know what will be the output, whether head or tail. Similarly, the same thing happens for the dice. There are out of six outputs, we are not sure which one we will be getting. Okay, so if you consider a coin toss or throwing a dice, again they can be classified into fair and unfair depending on whether the coin which you are using has some specifications. Say, suppose head will occur more times than tail, or the vice versa. Again, for the dice, if nothing like that is specified, then that means we are using an unbiased coin, then this is a fair coin toss, otherwise it is an unfair coin toss. Similarly, throwing a dice can be fair and unfair. So whatever it may, whether it may be fair or may be unfair, in all the cases we are getting, or we are getting in a real life situation a probabilistic behavior. Acha. Now, what is our task here? See, suppose this is a real life situation which is occurring. Suppose you are tossing a coin, you are getting some behavior which is probabilistic. That means you are getting some outputs which is probabilistic. Now, what we are trying to do, we are trying to simulate the same behavior by just designing an algorithm. Okay. Now, as we are dealing with probabilistic behavior, so it will be better to use the Monte Carlo method. Okay, so real scenario, under this we are getting the probabilistic behavior, and just we are trying to design a model, the simulating model, okay, via which we can produce this probabilistic behavior. Okay, that means we will produce a data set which will be accurate up to a certain level with the data set which will be obtained in the real life situation. So as we are dealing with probabilistic, so Monte Carlo will be helpful in this method, as Monte Carlo is dependent on random number generation, and random number generation means, as we have already discussed, we are generating real numbers. Up to our purpose we are considering real numbers only. Up to real numbers we are generating in an unpredictable way, and you just generate random numbers using any technique. Up to date we have learned two techniques as per our syllabus, so we can use any of these two, so as to get the random number generation. So the most important thing here we will be learning here today is how to you write down the algorithm for the Monte Carlo simulation so as to produce or generate, say, suppose the data set of a coin toss, or a fair coin toss, data set of a throwing a dice or an unfair dice, like that. Okay. Acha. So what will be forming the basic of this before I go into the formal idea which is expressed in the lecture material? I'm just giving a rough idea what we are trying to do there. Okay. So suppose let us consider the coin toss experiment. Okay. A fair coin only we are considering. Acha. So what actually we will do? So suppose we will consider the interval 0 to 1. Okay. So it is a real line interval. Okay. No problem in it. Then we are we are just halving it into two equal halves, 0 to 0.5 and zero point 0.5 to 1. Okay, and why two equal halves we are taking? The basis of that is supported by the fact that we have already the information that we are trying to simulate data for a fair coin toss. Okay, so now if I just divide it into two parts, then what we will do, we will assign. So suppose we will assign key, we will generate some random numbers in a way such that if my random number which I generate, or which I just get via some method, if it falls within 0 to 0.5, then I will say I am getting a head. Otherwise, it will not be a head. That means if it falls between 0.5 to 1, then it will not be a head. Now it is only a two output experiment. So obviously, if it not be a head means tail is the only possibility if you toss a coin. Okay, so in this type of two output measurement, it is enough or sufficient to analyze one output, because once I analyze one output, other output is coming as a complementary part. Okay, so no need of dealing it separately. Okay, so what is our just strategy here? We divide the whole interval 0 to 1 into two equal halves, and then assign key, if say suppose here I am taking key, if my point, or if your random number here p1 says 0.2, if you get, then I will say okay, corresponding to it the output here is occurring. Again say p2 equal to 0.7 here, it is greater than 0.5, then tail is occurring or not head is occurring. Okay, again P3 here 0.1, again head occurring. Okay, like this we will go on assigning. Okay, many points. Acha. So as soon as we are assigning these points, what is happening? He says, suppose I have got this one P1 as first. I am just considering another count. Okay, what count? Ki I will count the number of heads you are getting. So suppose I just repeat this random number generations 1,000 times. Okay, so out of 1,000 times, how many times you are getting the head? That means how many times the random number you are generating is falling within 0 to 0.5. Okay, so that count divided by total number of tries, if I say 1,000, then that count by 1,000 will give you the probability of getting a head. Now, as we know from the idea of statistical regularity, if we go on increasing the number of tries, then this probability of getting a head for a fair coin will approach towards zero point 0.5, that means half. Okay, similar is the case for the tail. Acha. That means what we have to do other than this random number generation, we have to do another thing. We have to count how many number of times you are getting the head. So I am just using the variable count of head. Okay, so here suppose I said P1 will be 0 0.2, then you are getting head, then I will put 1 here. Again, say for P3 you are getting 0 0.1, so again head, so I get 1 here. Again for 0.4 P4 you are getting again head, so I put 1 here. So you just repeat, go on repeating for 1,000 tries how many number of times you get the head, and then add up all this. This will be giving the count, and count divided by total number of tries, the total number of random numbers you are generating, will give you the probability of getting the hit. So exactly this type of idea is to be used when once we try to design the Monte Carlo algorithm for simulating the probabilistic behavior corresponding to a coin toss, a fair coin toss I am taking. Okay. Acha. Now the question is, if I now say, as I already said, coin toss can be fair, unfair, depending on whether you are using a biased coin an unbiased coin or a biased coin. So depending on that, the 0-1 interval is divided into two equal parts if you are doing a fair coin, and if you are considering an unfair coin, then it is divided into two unequal parts. And this division in the two unequal parts, okay, suppose I have the information or it is given beforehand, you have to simulate using some algorithm the data set of a unfair coin toss where the coin is designed in such a way so that it will give h more number of times, that will it will give head more number of times compared to tail. That means h is more probable than t. It can be one case. Another case is just suppose t is more probable than head. So if h is more probable than head, then what should we do? If we have this information prior to we develop the algorithm, before we start developing the algorithm, if we have this information, then what we will do? We will divide, as we said, we will divide the 0-1 interval into two equal unequal parts. That out of those two unequal parts, the larger one will be assigned for head. Say suppose here I took 0.5 to 0 to 0.5. If I know I have to design it for the coin toss where more number of heads can occur, then let me just take 0 to 0.7 for head and remaining 0.7 to 1 for tail, obviously. Then okay, same, just opposite can also happen. If you consider the tail can occur more number of times, then I can assign 0 to 0.7 for tail and then 0.7 to 1 for head, or 0 to 0.3 for head and 0.3 to 1 for tail. Okay, so this depends for which I am generating or for which we are designing the algorithm. Okay. Acha. So that is what I have just written here roughly. Acha. Now, as this is already I said, if it is coin toss two outputs, then analyzing only one is sufficient. But this is not the case if we have more than two outputs. For example, we take the throwing of a dice case. Okay, so suppose if you consider throwing of a unbiased dice also, that means a fair throwing of a dice. Okay, so 6 outputs are possible, and each of them is possible equally. That is equiprobable. If you consider an a fair dice throwing, then all the outputs are equiprobable. So in that case, that means in unbiased case, what we will do? Again, we will take the 0-1 interval. Okay, what is our main task? In simulation, our main task is to simulate random numbers. Where these random numbers will lie? Again, between 0 and 1. And how we are going to divide the 0 1 1 0 1 interval into now 6 equal parts corresponding to 6 outputs that can occur. So suppose 0 to 1 by 6 I take for 1. That means if any number I generate, random number I generate, if it falls within this interval 0 to 1 by 6, that means a point, but 0.133 like that. Okay, but sorry, 0.166 like that if you get. So here if it falls within 0 to 1 by 6, then I will say ki okay, the phase occurring one has the phase 1 has occurred. If it falls within 1 by 6 to 2 by 6, then I will say ki phase 2 has occurred, and likewise. So 0 to 1 by 6 is assigned for phase 1, 1 by 6 to 2 by 6 for 2, and likewise ultimately 5 by 6 to 1 for 6. Achha, let me mention ki you may ask ki why suddenly I am using 0 to 1 by 6 for 1. You can just reshuffle between them, no matter. I'm just following the, this ordering. First one I will consider, then 2, then 3, then 4, then 5, then 6. So accordingly I'm taking 0 to 1 by 6, then 1 by 6 to 2 by 6, then 2 by 6 to 3 by 6, 3 by 6 to 4 by 6. Like this I am taking. Okay. You may just jumble up here. No problem will be there. Okay. So suppose one can take, if it falls within 0 to 1 by 6, I take 2. And for 1 by 6 to 2 by 6, you can take 1. No problem with that. The main thing is that you have to divide the whole interval into equal parts, because we are considering an unbiased dice here. Okay. So what will happen? We will randomly generate numbers. Okay, all lying between 0 and 1 using any of random number generation. Okay, and then the algorithm will say ki if it is falling within 0 to 1 by 6, then phase 1 is occurring. And then what we have to use counts here, right? Just as we did for the head part of the coin, here also we have to use counts, but now more than one count is required. So count 1 for 1, count 2 for 2, count 3 for 3, likewise. So more than one variable is required for counting. And for each of them, we will just go on adding just as we have considered here, depending on what output you are getting. Okay. Here only count of head was there, but here as in dice string more than two outputs are there, so we have to count each of the outputs separately. Okay. Otherwise, we cannot analyze all the outputs, right? So once you do that, same thing you can just use to get the required probability or the probabilistic behavior which you are generating via this algorithm. Okay. Now let us go with this idea. Let us approach to the material. Okay. So we are trying to do this as I already said, and we know ki this number of favorable events, the total number of events. If you increase the number of events, total number of events, then this is going towards or tending towards the required or probability. Okay. That is what I said about the statistical regularity, and this is your giving the frequency definition of probability. Okay. Acha. So these are some of the examples of probabilistic models: flipping a fair coin, rolling a fair die or a pair of dice, and roll of an unfair die or a pair of unfair dice. Okay. Acha. Mainly we will be doing this one, then rolling of a fair die, and then rolling of an unfair die. Acha. So a fair coin, if you are taking, then we are, as I said, it is to be divided. The whole interval 0, 1 will be divided into two equal in parts. That is here controlled by this fx function. Okay, where x is a random number between 0 and 1. How this fx function is working? It is assigning head. Just as I said, it is assigning head whenever your x is what? A random number between 0 and 1. Whenever x is lying between 0 to 0.5, fx will assign head. And if it falls between 0.5 to 1, fx will assign tail. Okay. Acha. Now you see the fx assigns the outcome head or tail to a number between 0 and 1. Okay. And this will be forming the basis for the Monte Carlo algorithm. Okay. Acha. And we want to take the advantage of the cumulative nature of this function as we make random assignments of number between 0 and 1 in the long run. We expect to find the following percent occurrences. That is what I said. You just go on putting the number of, or you go on counting how many number of times your x is falling within this interval. Then you will get the number of occurrences of head, and that one divided by total number of trials will give you the required probability. Okay. So random number interval, if x is less than 0, then cumulative occurrence is 0. Okay, because if you're we are considering 0 to 1 interval, so if it falls below 0, we won't consider that. If it falls above 1, then also we won't consider that. Okay. So that's what they're saying. If x less than 0, then cumulative occurrence is 0, percent occurrence is 0. All this is said with respect to the occurrence of the coin toss. Okay. So if x is falling within 0 to 0.5, then cumulative occurrence is 0.5, and percent occurrence is also 0.50. Okay. And again, if x falls between 0.5 to 1, then it will take 1, and here the percent occurrence is 0.5. So what we are doing here, we are going on adding the whatever probability or whatever chance you are getting here. Okay, just as we used to do this for the distribution function. If you recall back from the probability theory, we do it from the distribution function fx, okay, minus infinity up to x, whatever x you are taking. So directly we are not going to use it, we are just giving the idea how we are going to just generate the algorithm. Okay, so most important part is this one, the Monte Carlo fair coin algorithm. Okay, so let us see how we are designing it. So input this total number n of random flips of a fair coin to be generated in the simulation. That means how many number of coin toss you are doing. Okay, so let us denote it by small n. Output, what we are trying to output, as I said, I am trying to output the probability of getting ahead when we flip a fair coin. This is very important, fair coin. Okay, because we know ki depending on whether it is fair or unfair, the division of the 0 1 interval will matter. Okay, to initialize, that means at the initial we have to take some value of this variable, so it is an integer variable. Okay, counter, what I said about count, they are using just naming it counter, no problem, you can use that counter name also. So counter equal to 0. So before the game starts or before this flipping start, neither head has occurred nor tail has occurred. As head has not occurred, so counter equal to 0. Okay, now flipping is starting. So flipping is starting in a real life situation that I have to model or I have to think whenever I am trying to compute it or I am trying to design the logic flow. So for I equal to 1 to up to small n, that means number of flips you are considering, repeat steps 3 and 4. That means do steps 3 and 4. What is step 3? As I said, obtain a random number xi between 0 and 1. So this part you see, random number generation is involved. Okay. Acha. Now, once you generate a random number xi, then you judge whether it is, or you just see whether it is falling within 0 to 0.5 or not. If it is falling within 0 to 0.5, what we have considered via the function fx, head should be occurring, or we will say ki, okay, head has occurred. Okay, or my machine or the model will say ki it has occurred. I repeat here once again ki when I am simulating the model, I have no coin in my hand which I am tossing. Okay, so this coin toss is a real life situation, and we are trying to give a virtual uh, platform where we are just going to give a model which will replicate the data. Okay, but that model and the coin toss are separate. Okay, so here I am generating random numbers, and depending on the random numbers what I am observing, I will write or I will output accordingly. So if my random number which I am generating, say suppose x1 is first generated, if x1 falls within this, then I will say okay, the machine will say okay, count, you have obtained one head. So counter, this records counter plus 1. Counter was initially 0, so here you get 0 plus 1, so 1. Okay. Otherwise, leave counter as it is. Otherwise means what? If not, that means else. That means if xi falls within 0.5 to 1, then what? Head will not occur because fx we have designed like that. So in that case, counter, leave counter as it is. So counter was 0, it will be remaining 0 only for the first step. Again for the second step x2, again the same thing we will do. Okay, x2 means another random number generated. So here also I will check whether it is falling within 0 to 0.5. If it is falling, then whatever counter value was initially in the first for x1, it will just increase by 1, and if it is not falling, it will remain as it is. Okay, this is quite obvious, I think you can follow this very well. So ultimately what I have to do, I have to output the probability. That means I have to use the frequency definition of probability. That means this I will have to use number of favorable events by total number of events. That is obviously what you know from the probability theory itself. So for that thing, I need the counter and total number of trials. So calculate p head, then probability of head equals to counter by n. simply. Okay, then output this value, so output probability of heads, and then stop. Okay, so you see throughout I never mentioned about tail. Why? Because if head is not occurring, the otherwise part is controlling the tail factor. Okay, because only two outputs are possible. If head is not occurring, then obviously tail is occurring. No need to analyze it separately. That's what they are doing here. Acha. Here they have given a data set. Figure 2.5.3 illustrates our results of various choices of n of random number generation xi. Now you see what they are doing. First, they are doing 100 flips. That means in real life you are flipping the coin 100 times, and in my model, 100 random numbers are generated lying between 0 and 1. Number of heads occurring 49. So what is the percent head? 49 by 100. So this one. Now you increase it, see 0.51, and this will oscillate. And what they're trying to show here, if you increase the number of trials, this percent head, that means this is a probability actually, is just trying to tend towards the actual one, or the use the well-known one, that is zero point 0.5 for a fair coin toss. Probability of head occurrence is zero point 0.5. So it is trying to head towards that thing. Okay. So up to this, what is our main important thing? This algorithm is the main important thing. Okay. Okay, now let us go to the rolling of a fair die. That means one die is there, consists of the numbers 1, 2, 3, 4, 5, 6 corresponding to the faces occurring. Acha. The probability as before, total number of trials by a number of occurrences of the particular number, any one of this you choose, say suppose 4, by total number of trials. Okay, that's simply the probability definition here. Nothing to be worried about or nothing to discuss new here. Just the probability definition we are using. Okay, for the discrete case. Now comes the algorithm. Okay, so as I said, or just we have done before, what will be the input? How many number of times you are rolling the die. So total number ends of random rolls of a die in the simulation. What is the output? I need the probability. Probability of what? Probability of percentage, the same thing. For rolls of 1, 2, 3, 4, 5, 6. There is probability of each of the output I require. Okay. Acha. Then initialize counter 1 through counter 6 to 0. Counter 1 through counter 6 means what? As I said, here more than two outputs are there, so definitely we need different counters to count the number of occurrences of the different outputs. So counter 1 for face occurring 1, counter 2 for face occurring 2, that means counter I for face occurring I varying from 1 to 6. So each of this counter, before I start rolling the die, that means in model, before I start randomly generate the numbers, before I start generating the numbers, I will initialize all the counters to 0. Okay, so that is what this is the initialization step. Then for I, starting from 1 to up to small n, that means how many number of trials you are doing the throwing the dice, or how many number of times you are randomly generating the numbers. For each of those steps you have to repeat the steps 3 and 4. So again, what is the our task? Random number generation. So here the random number generation is involved, and random number should lie between 0 and 1. Okay. Acha. Then again, if xi belongs to this intervals, then increment the appropriate counter. What are the interval division? As I have shown, if it lies between 0 to 1 by 6, then counter 1 will be counter 1 plus 1. Counter 1 is recording the face occurring 1. Okay. Again, counter 2, if your random number fall within this range, then counter 2 will be increased as it is. Similarly, all this will be following this pattern. Okay. Acha. So suppose xi is falling within 1 by 6 to 2 by 6. That means what? As soon as we get the random number, see the random number is falling within this, then we become sure, okay, then this corresponds to phase 2 occurring according to our model. Okay, according to our simulation model, this corresponds to phase 2 occurring. So counter 2 will be increased by 1. That means what about the remaining counters in that step? That means, so suppose x5 is occurring, that is I for I equal to 5, x5 is lying within this range. That means at the fifth generation random number, the fifth random number is falling within this counter. That means phase 2 is occurring. That means the remaining phases are not occurring. So all the remaining counters will remain as it is. So that's what they're saying. If xi belong to these intervals, that means if it belongs to this interval, definitely they cannot belong to the remaining intervals. Then definitely counter 2, when it increases, all the other counters will remain as it is. Okay. And then calculate probability for each row by the same formula, the probability definition using the frequency definition of probability actually, counter of j by n, then output all the probabilities and then stop. Similarly, this type table is given the experiment once performed and the simulation trial where dice value is 1 2 3 4 5 6 and the number of repetitions you are taking 10 100,000 10,000 and then 1 lakh, and the expected results are like this 1.667 like this. Okay, so this is when we throw a die, fair die, what happens? Probability of each any phase occurring is 1 by 6. So see, if you are going on increasing the for the first time, they are much deviated from the 1 by 6 result. Okay, if you increase the trial, then they are lesser deviation because 1.19 is closer to 0.16 compared to zero point 0.3. Same is the for this case. Again, if you take 1,000, even it gets more closer. 10,000 much more closer, and 1 lakh it is almost 0.1667, which is the expected result. Okay. Acha. Now for an unfair die, role of an unfair die, what we can do? Here, as I said, the biasness will be given as an information prior to simulate the result or simulate the algorithm. Suppose roll value 1, that means phase occurring 1 will occur with probability 0.1, 2, 3, 2 also 0.1, but 3, phase 3 is more probable. See, 0.2 is assigned to it. 4 is yet more probable, 0.3 is assigned. Again, 5, 6 is assigned 0.2 and 0.1 respectively. So with this information in our hand, this will try to give us the idea how should we divide the 0 to 1 interval. Okay, so now let us see. So this is the value assignment we are doing. If it falls between 0 to 0.1, then we'll check if phase 1 is occurring. Up to our model we are saying this. Okay, that means we will be using this one to simulate the algorithm. Again, if it falls between 0.1 to 0.2, then 2. As another thing, let me mention, quite obviously you have might have noticed already, key 1 will be closed interval. That means if you consider 0.1 within this one, then definitely 0.1 will not be considered here. That means it will be an open interval. So each of this interval, excepting the first one, okay, will be semi-open interval. Starting point will be open, ending point will be closed, or you can interchange also. In that case, this one will be semi-open again. Okay. So up to this, let us take 0 to 0.1 as a closed interval, and then anything greater than 0.1 to 0.2, 0.2 to 0.4, and likewise. So now you see, this value assignment corresponds to what is given here. 0.1 probability of rolling and getting roll value 1, that means phase occurring 1, 0.1. So what I take in the 0 1 interval, that means here instead of taking 1 by 6, I take up to 0.1, 0 to 0.1. If I get any random number, I will say phase 1 is occurring. Same is the case for 2 also, 0.1 to 0.2. Okay, I will say phase 2 is occurring. But from 0.2 to 0.4, okay, I will say key phase 3 is occurring. And now you see, if you add this all up, again the cumulative nature is there. Okay, if you add this all up, ultimately we will get 1. That means the whole interval is covered once I consider all the 6 outputs. Now, how this interval is covered depend on whether you are using a fair die or an unfair die. As I'm using an unfair die here, so this division is not at all equal. Here I'm taking 0 to 0.1, then 0.1 to 0.2, then 0.2 to 0.4 for 3, and 0.4 to 0.7 for 4. Okay, so that expresses how we are designing or how we are using the information given here. So simply, this division will now be used in these algorithms. So input and output is the same thing. Initialization again the same thing. And up to step 2 all are the same thing. Only what will up to step 3 in fact, because random number will be generated by any of the methods we know for random number generation, such as this linear congruence method or least square method. So nothing to do with this problem we have to tackle here. So up to input, up to step 3, everything remains the same, just as we did for fair die or unfair die. Does not matter. But what will change here? Step 4 will change here. If xi belongs to these intervals, then increment count the appropriate counter. In fact, the arrangement pattern also does not change. This counter increment does not change, obviously. But what changes? This interval division. If xi falls within this one, then counter will increase. If xy falls in this two, 0.1 to 0.2, then counter 2 will increase. But here, see, zero point 0.2 to zero point 0.4. So 0.2 to 0.4, zero point 0.4 to 0.7. So see, these are not the equal thing. And how we are getting this? Just because we are using this part of the information provided. So this information provided from the real experiment is used in the simulation model here. Okay, so that is the main thing for the unfair die, or the extra thing you may say for the unfair die compared to the fair one. Okay, only this interval pattern will change. Otherwise, this counter thing will again remain the same, and ultimately this probability calculation again remain the same, and you just output the probabilities, and the stop means the algorithm ends here. And results from a roll of an unfair die is again given here. Okay, so this is die value. This is for the results for 100 trials, 1000 trials, 5000, 10,000, and 40,000 trials. Okay, and as is an unfair die, so obviously it is expected ki you won't be getting 0.16. Okay, so whatever these expected results are, you see the number of trials, if I increase, these values are becoming closer to this one compared to say 100 trials, 0.080. It is much more deviated from 0.1 if you consider 0.0948. It is 0.0948 is closer to 0.1 compared to this one. Similar is the case for this one. So that means it obviously just implies the same thing, that if you increase the number of trials, that means you just generate more and more random numbers, your expected results is much more likely to be obtained. Okay. Acha. So let us stop here with this one.